All right, so in the previous video, we discussed ratio of uniforms and a few examples involving ratio of uniform. The exponential example and drawing from Gaussian or normal distribution. Now, we also looked at code for this, but I wanted to switch completely to R to explain a little bit on what exactly is going on. Now, I will admit that intuitively understanding ratio of uniforms can be a bit challenging. It's not very clear, how the intuition of this region C over here is and how it's connected to the sampling, the target distribution that we want to sample from. I admit that that sort of connection is not very intuitive, but maybe the plots that we discussed last time can be a bit helpful. So I wanted to go over that a little bit of code involving ratio of uniforms. So our target, for example, here is to obtain draws from the exponential distribution. And we have, this is the PDF of of an exponential distribution with rate parameter lambda. And C, our region C is nothing but, U comma V such that 0 is less than equal to U, less than equal to e to the power minus V by 2U. Right? So that's our region C. And the way the way ratio of uniforms works is that this region C can be a bit complicated. And so, we draw value, we bound the region C by a particular box, and then we draw from the box to see whether we have indeed drawn a value or a point in the region C or outside the region C. And then we implement accept reject based on this region C. If we get a draw from this region C, then we take V, the second component, by U, the first component, V by U, and V by U becomes a draw from F, right? That's the paradigm of ratio of uniforms. So we discussed for the exponential distribution case, we discussed how do you actually find the enclosing box. And we found that the enclosing box on the x-axis or the u-axis is 0 and 1, a equals 1. So on the x-axis we had 0 and 1, and on the y-axis we had 0 and 2 by e, 2 divided by e. Okay, so the enclosing box was going to be on the u-axis from 0 to 1 and from 0 to 2 by e. All right, so now we'll implement accept reject for this. Okay. So for ratio of uniforms for this. So for ratio of uniforms for this exponential 1 distribution, so this is my target, and I want to get 1,000 samples. So now every time I sort of make a little bit of change in the style of code that I'm going to show you. Previous few times what we've done is we've made functions that we call to obtain samples. And here I'm showing you code that is not written inside of a function. There's no particular reason for me to change from one style of the code to another style of the code. I'm just, through the R code, I'm also trying to demonstrate to you the various ways we can actually code different type of algorithms or the different styles of coding techniques. Okay. So instead of making a function this time, we just say that we want 1,000 samples. Capital N is the number of samples, and these will be saved in samples. But the actual samples from exponential will not be saved in the samples. The accepted values in the region C will be saved at the sample. So not draws from the exponential target distribution, but draws from the region C that we finally accept will be saved. And then when we take the V component of those samples and divide by the U component of the samples, we should get a draw from exponential. Okay. So n equals 0 means so far I have not implemented and I have not gotten any accept or reject done. So as in I have not gotten any points from the region C as yet. And I'll keep doing this until I get 1,000 points in the region C. So while n is less than capital N, I keep doing the following. Prop.u is a random uniform between 0 and 1. Prop.v is a random uniform between 0 and 2 by e. So this is, uniform between 0 and a, and this is uniform between b and c, where a, b, and c are from the calculations that we have done here, right? Now, having obtained this point, we check if the point u comma v or prop dot u comma prop dot v is in the region C. Okay, so if prop dot u is less than equal to e to the power minus prop dot v times 2 prop dot u, this is us just checking whether u and v together satisfy this condition. If it does, if they do, then we have a region, we have a draw from C. Okay, so if they do, then n is equal to n plus 1, indicating we have indeed gotten one observation. That's an observation from C. And we save that prop dot u comma prop dot v in the nth row of the matrix that is samples, right? The nth row is going to have this as as the entries into that row. Okay, right? And when I do this, okay, when I do this, I'm going to get, a histogram, let's say, of okay, not yet. So let me not show you the histogram. Let me actually show you what I'm going to show, what I plan to show you next. What I would do is just to understand what this region C looks like, I'm going to plot all of the points that have been accepted on the region C. Okay, so for example, here's what I'm going to do. Plotting the accepted points is what I'm going to do. So I just put a comment in so that we know what we're doing. And if I do plot of samples, means it's going to take the first column of samples and plot it on the x-axis, second column of samples and plot it on the y-axis. So that part is fine. And if I just do that, if I plot samples, it's going to take a second to understand what I'm asking from it. And look, it just plots all the samples. So on the x-axis, I have the u component. On the y-axis, I have the v component. And if you sort of look at the region that it covers sort of this lower bounded by 0 on this side. And then this is exactly what the region might look like. Okay. And so I'm going to change the style of the plot here by saying PCH equals 16. So it's going to make the actual plots will be sort of these filled in dots. I like those points. And what I'm going to do is I'm going to also make my enclosing box C. Not C, but the enclosing rectangle from which we were doing accept reject, which means I need a sequence of vertical lines and a horizontal line. So I'm going to AB line makes sort of straight lines in R. So the vertical lines I need at 2 points, I need at 0, right? And then the second vertical point I need at 1. So I need at 1. And the horizontal lines I need at 0 again, because I have a 0 horizontal line here. And the other one I need at 2 by E, which is exponential 1. And let's just, for the sake, color this in blue. And let me do a thicker line. So line width is 2. And when I run this, I sort of get this enclosing box. Right? So this is exactly what's happening in my accept reject. Okay. Right? So whenever I get a point that is accepted or that is proposed outside the point, outside the line, then that point is rejected. Otherwise, it's accepted, and these are all the accepted points. Okay, there must have been points outside as well, but they happen to not be accepted. Okay. But this region C is not very intuitive, right? We have u on the x-axis and v on the y-axis. But what does this mean? So if I take, any particular point here, let's say I take this point, then this point, if I take its v component and take its u component and I divide, then that corresponds to the draw on the exponential. So what I'm going to do is I'm going to color code points that I have here in different regions that correspond to different points on the exponential. Okay, so what I mean by that is I do the following. I break up the region C into various segments, And exactly how, I'm not going to explain. Please, if you're really interested in how I'm making these plots, please do take a look at the code, and hopefully it'll give you some information about what's going on. But the code is a little complicated for me to explain. And so I'm just going to run it and you'll see what I'm trying to do. Okay. So now let me just increase. So here is what C looks like. So C has the bound region like this over here. And I draw my sort of AB lines, which is so I draw my AB lines, which turn out to be this enclosing box. Okay, and then I add my points. These are all the points that I saw in the previous plot as well, right? Now it's squished, of course, but now what I've done is I've color coded the points based on certain criteria. So these are the same points, but they're in a different color based on something. And if I take this second component of the samples and divide it by the first component of the samples, which means this is V by U, then X is going to be a draw from V by U, from the exponential. Okay. And so if I calculate this, and I also calculate the density of the density of the exponential at this particular point. Remember, this is density at rate equals 1 by default because it's exponential 1. And then I plot x and y, the sample that I obtained, and its density value, and then I color its density value based on the corresponding color here. What it looks like is the following. Okay, so this is really what I was trying to get at, is what I have is I have these regions over here that if I take any point in this region and I take in this region C and I plot V by U, then that V by U ratio corresponds to these segments of the density, right? Which means that any point that lies over here in the exponential will correspond to this point in C. Now, if you notice that outlier points, these two yellow points or these pink points, really lie very close to the corner of the C region over here, to this very corner, very close to zero, is where some of these points lie, right? And the farther we move away from this region, the more it's in the higher tails of the density, right? And that's because the regions close to this U is small, and so if U is small close to this, then V is also small. Sorry, no, when U is really small close to this, then V by U means U is small in the denominator, so V by U really is large, right? And I know it's an exponential one, so it doesn't have too many large values. So V by U being large means those are outliers, okay? Now I can repeat this process again if I want a different exponential. So instead of exponential 1, I can think of an exponential lambda, and I can set lambda equals, let's say, 10. Okay. Then in this case, this is e to the power minus lambda x. So this will be e to the power minus lambda times prop dot v by 2 prop dot u, right? Square root e to the power minus lambda x. That's exactly what this would be. So I'll get lambda over here, and this is going to start to look like my ratio of uniforms for a particular value of lambda. Okay, I can draw the region again. Looks a bit similar, but now the height has changed a little bit. Okay, so I draw the colors again, and look. Oops, I guess I should change this to minus 2 by lambda u times, I think, lambda. Let's try that again. Oh, I think divided by lambda, if I can remember correctly. If not, then we leave the code be. Yeah, there we go. Yeah, I think so. I had to change also how the curve looks like as a function of lambda. Okay, so I get these points. And then I don't have rate equals 1, I have rate equals lambda now, which is in this case 10. And look, I don't get colors for some reason. I guess the way I've made the function, it's made specifically for lambda equals 1, so I don't necessarily get the colors. So the colors would work best when lambda is equal to 1, so I'll let lambda equal to 1. It's just the way I've made the function and how the colors appear. Okay, but it can be generalized into other values of lambda as well. Okay, we can do the same thing for the Gaussian case. So if we go back to our notes, just to visualize what this region C looks like, this is what our C function looks like for Gaussian, and we were able to find the enclosing box where this was A, this was B, this was C. We solved for A, B, and C, and we basically got this. Okay? And so we've gone through the code already. I just wanted to help you take a look at the region A, the ratio of uniforms region. So if let's say theta is 0 and sigma squared is 1, so my target is the standard Gaussian, okay, then I can plug in what sigma squared is here, and I can plug in what it is here to get the value of B and to get the value of C. That'll give me the enclosing box, right? And so this is exactly what I'm doing in the code at this point. Now, I know I want 5,000 samples now from this Gaussian. Let's change it to 1,000. And again, I'm storing my samples. Now I'm storing prop.u and prop.v. Then I'm checking if the sample drawn is the uniform samples on the rectangle. Is it inside the region C or not? If not, if it is, then I go ahead and accept, and I have gotten one acceptance, right? So all's good once I've gotten an acceptance, and I keep doing it until I get capital N acceptance. Okay. And then I use the same thing. So exactly how I'm color coding and making these plots, you can take a look at it. This code will be available to you. You can take a look at it. But for now, I'll just leave it be. I'll just make you the plots, and you can see what they look like. So this is exactly what happens. So this is the ratio of uniforms region C for normal, 0, 1 in this case. And look, the closer you are to 0, 0, the origin where u is equal to 0 and v is equal to 0, in this case, on this side, you are on these outliers, and on this side, you come into these outliers. Right? So the closer you are to the origin again, the more closer you are to being an outlier, even in this case. And then there are strips of the region C that are devoted to areas of high probability or low probability. Okay, that's basically how this works. Now I can change, if I change sigma squared to 100, really large variance, some of the shape will change a little bit. So let's see what the shape looks like when I change. Oops. Oh, looks like 100 is too large to visualize. So let's look at 10. There we go. So now, basically the scaling changed. So if I go here, the scaling has changed a little bit because look, this is going from, -3 to 3, and now I'm going from roughly -10 to 10. So it's just the scaling that has changed. However, if I take sigma squared back to 1, and if I take mean to be 5, okay, and then I draw what the C region looks like and what the corresponding samples drawn from that region look like, then look, this is exactly what this becomes when C is equal to, when theta is equal to 5. Now the region looks very different. You don't have that sort of circular type structure, but you have a little bit of an oblong, elongated structure when the mean has changed. We can change the mean even further. Let's say I make it -10, and I run this again, and now it's turned into the opposite direction. Again, it's the same idea of what the region C is going to look like, but it does look fairly different from the usual ones that we're used to seeing. Okay, so that's just to give us an insight into what the region C looks like. Now, it is still true that this doesn't really give us a lot of insight about what's really going on, but hopefully it's helpful to understand what's happening in the region C and how different points are corresponding to different parts of the draws from our distribution of interest.